Hello everyone, James Boyce back again for RL Education. Today we're going to be looking at circular motion, specifically in the vertical plane. What we're going to be wanting to do is find out what forces do we need on this to have it maintain motion throughout this circle. Before we get into that, we just need to talk about general circular motion. So, circular motion, we have object moving around a circle. For example, in this direction, it's going to travel all the way around like this. And as it does that, we know that at any one given point, like where it is now, for example, its velocity will be tangent to the circular path it's taking. So in this case, velocity will be in that direction. And its acceleration will be always towards the center of the circle. So in this case, like that. The acceleration, and that there is the velocity. Now, as it moves around the circle, for example, if it was over here instead, then the velocity would be like this, and the acceleration would be still towards the center, but now like that. A like so, and B like so. If you look at the next path that these balls are about to take, you can see that this acceleration makes sense, hopefully. For example, this blue ball here that we're looking at first, it's moving this way, which will keep it along the bottom here. But then as it continues that way, it needs to start to move up because this circle is moving up, right? And therefore the acceleration is up. So it's gaining upwards momentum, upwards velocity, and the circle is going up. So that makes sense. Similarly, if you look up here, right, as it goes forward, it's going to need to start going down, and the center of the circle is going to be pointing down at that point. You can apply the same logic to any point around the circle. Now, what we're going to need for our problems is a formula that tells us how big this acceleration is. And so what we have is this. Acceleration for circular motion equals v squared over r. R is the radius of the circle it's going around. V squared is obviously just speed squared. We also know from our basic laws of motion that Newton's given us that force always equals mass times acceleration. Therefore, the force on a ball as we move around circular motion is going to be given by just m times v squared on r, because that's what our a is. So v squared over r. And it's important to note that these F equals ma laws, force equals mv squared on r, are always going to be net force. So this is net force, and this here is also net force. All right. Now that we know these, we can go into doing an actual problem, finding the forces on an object as it goes around a vertical circle. So for today's example, what we're going to be looking at is this cart here moving around this vertical circle. What we're going to be trying to find is if it moves around this circle at a constant speed the entire way with just gravity and normal force acting on it, then what is the normal force going to have to be to make sure that it maintains this motion throughout the circle? Okay, rearranging the setup a little bit so we get a little bit more space. So, from the preliminary work we did, we know that if this cart is going to maintain circular motion around the circle, that its acceleration must be given by v squared over r. And therefore, its net force must be given by mass times acceleration, in this case, m times v squared divided by r. For the problem we have here, mass is 20 kilograms, velocity is 15 meters per second, and our radius is 5 meters. So our net force is going to be 20 times 15 squared divided by 5. 20 divided by 5 is 4, so that means our net force is 4 times 15 squared. And 15 squared is 225, times by 4 equals 900, so our net force must be 900 newtons. Now, forces are vectors, so net force being 900, we'll leave it as positive for now, which will be fine as long as we keep that consistent throughout the problem. And we know that the net force is going to act the same direction acceleration acts, which we know is always towards the center of the circle. So our net force here is going up, and it's positive. We also know the net force is not a real force of its own, it's just the addition of all the other forces acting on the object. In this case, we're only thinking about gravity and the normal force. So we know gravity always acts down. In this case, the force of gravity is just going to be given by the mass times gravity. So in this case, 20 times 10, 200 newtons. And we know that the normal force always acts in opposition to the surface you're standing on or you're moving across. In this case, the cart's coming down here, and so it's resting against this surface here. Opposition to that will be a force acting upwards, like so. So we now know, okay, net force equals the addition of all of our forces, in this case, normal force, plus gravitational force. However, we need to keep in mind what directions these things are in. So, our normal force is moving up, our net force is moving up. We've already said that the net force is going to be positive. So in this case, instead of saying plus Fg, I'm actually going to say minus Fg. And this equals 900 newtons. Therefore, we rearrange this, we get normal force equals 900 plus force of gravity. Force of gravity is 200 newtons, 900 plus 200 is 1100. And so, for this cart to maintain circular motion around the track, the normal force is going to have to be 1100 newtons. For our second question, we're going to be trying to apply the exact same principles, but this time to the cart when it's on the top of the circle. Again, we're assuming it's maintaining this motion using only normal force, gravitational force. So, same as the last problem, A is going to equal V squared on R. Therefore, net force is going to equal mv squared on R. But we already found out what that was last time, right? So we know that the net force is still going to have to be 900. However, in this case, we know that the cart is accelerating still towards the middle of the circle, but that means now the cart acceleration is actually downwards. So, seeing as this is a new problem, I can redefine what my positive and negatives are. I'll say that net force again is positive, but this time that means it's going down. Again, we need to think about the two forces we have. We've got gravitational force, which is always going to act down. And again, this is 200 newtons because it's just going to be the mass 20 times 10 for gravity. We also have the normal force, which is always going to act in opposition to the surface we're on. In this case, the cart's coming around. Surface is here. The opposition to that surface is also downwards. That means that the normal force will also act down. I'll just give myself a little bit of space to write it. Net force is now over here, still that same arrow, and then normal force is over here. So in this case, every single force is acting down. Again, net force is going to be the addition of all of my forces. So normal force plus gravitational force. In this case though, the net force is down, the gravitational force is down, and the normal force is acting down. We defined this downwards 900 to be positive, so all of these forces are going to be positive. We know this equals 900, and therefore our normal force equals 900 minus Fg. Normal force equals 900 minus 200 is going to be just 700 newtons. And so we can see that the normal force here is actually less than the normal force was in the previous question. And that's because in this case, the gravity is actually contributing to accelerating you around the circle. It's helping you go downwards. Whereas before, we need to accelerate up, and so the gravity is working against us. And so that's why this is smaller than last time. For your homework question this week, we have a skater who weighs 80 kilograms traveling over this perfectly circular hump of radius 10 meters at 5 meters per second. What I want you to find is the normal force he experiences as he moves over this hump, specifically at the point where he's at the exact top of the hump. We also want to know what the normal force would be if he traveled at 15 meters per second instead of 5 meters per second. And then comment on what this means physically, the answer you get in part 2. Best of luck with that, and as always, leave any questions in the comments.